If you thought the northern lights were impressive on Earth, think again. Jupiter has its own version of our aurora, but it is so high energy that it is made up of X-rays instead of visible light. When triggered by a solar storm, Jupiter's aurora can cover an area larger than the Earth's surface. For the first time, a research group led by UCL has looked at what happens to Jupiter's X-ray aurora when a giant solar storm arrives at the planet. The study, published today, has described the group's findings that were made from data collected at NASA's Chandra 10-Ray Observatory, a space observatory that was launched in 1999. The researchers discovered that solar storms trigger Jupiter's intense northern lights by generating a new X-ray aurora that is 8 times brighter than normal. They are hundreds of times more energetic and much bigger than Earth's. Lead author and PhD student at UCL Mullard Space Science Laboratory, William Dunn. Earth's surface would comfortably fit inside Jupiter's aurora. Whereas the chemistry in Earth's atmosphere is controlled largely by the Sun, Jupiter's aurora are so bright and powerful that it is them that control the chemistry in Jupiter's atmosphere, much more than the Sun does. So if you looked up from Jupiter into the sky, you would see the aurora stretch across the sky as far as the eye could see, and it would be much brighter than the Sun, even during the day. If your eyes could see the X-rays, you would also see it pulsing, going very bright and then very dim every 45 minutes, or, if a solar storm was occurring, every 26 minutes. It's also quite warm because it gives off lots of infrared radiation. There is a constant power struggle between the solar wind and Jupiter's magnetosphere, said Mr. Dunn. We want to understand this interaction and what effect it has on the planet. By studying how the aurora changes, we can discover more about the region of space controlled by Jupiter's magnetic field, and if or how this is influenced by the Sun. Understanding this relationship is important for the countless magnetic objects across the galaxy, including exoplanets, brown dwarfs and neutron stars. The Sun constantly ejects streams of particles into space in the solar wind. When giant storms erupt, the winds become much stronger and compress Jupiter's magnetosphere, shifting its boundary with the solar wind 1.2 million miles, 2 million km, through space. The study found this interaction at the boundary triggers the high-energy X-rays in Jupiter's northern lights, which cover an area bigger than the surface of the Earth. The impact of solar storms on Jupiter's aurora was tracked by monitoring the X-rays emitted during 2 11-hour observations in October 2011, when an interplanetary coronal mass ejection was predicted to reach the planet from the Sun. Interplanetary CMEs are massive bursts of gas and magnetic field that arises from the solar corona and is released into the solar wind. In 2000, one of the most surprising findings was a bright hotspot of X-rays in the aurora which rotated with the planet, added Mr. Dunn. It pulsed with bursts of X-rays every 45 minutes, like a planetary lighthouse. When the solar storm arrived in 2011, we saw that the hotspot pulsed more rapidly, brightening every 26 minutes. We're not sure what causes this increase in speed, but, because it quickens during the storm, we think the pulsations are also connected to the solar wind, as well as the bright new aurora. The scientists used the data collected to build a spherical image to pinpoint the source of the X-ray activity and identify areas to investigate further at different time points. These findings will complement NASA's Juno mission arriving at Jupiter this summer. The mission aims to understand the relationship between the two biggest structures in the solar system, the region of space controlled by Jupiter's magnetic field and the region controlled by the solar wind. As part of the mission, Juno will investigate Jupiter's relationship with the Sun and the solar wind by studying its magnetic field, magnetosphere and aurora. The UCL team hoped to find out how the X-rays form by collecting complementary data using the European Space Agency's X-ray Space Observatory, XMM Newton, and NASA's Chandra X-ray Observatory. We've only ever seen the day-side aurora of Jupiter though, because when you look from Earth that's all you can see, Mr. Dunn told Mail Online. This means that we have no idea what is happening on the night side. Juno will provide the first opportunity to see the aurora on Jupiter's night side. As to what it will look like, your guess is probably as good as mine. This is sort of a strange idea though, because at Earth we're used to seeing the northern lights at nighttime. Comparing new findings from Jupiter with what is already known for Earth will help explain how space weather is driven by the solar wind interacting with Earth's magnetosphere, said Professor Graziella Braun-Doherty-Raymond, From UCL's Mullard Space Science Laboratory. New insights into how Jupiter's atmosphere is influenced by the Sun will help us characterize the atmospheres of exoplanets, giving us clues about whether a planet is likely to support life as we know it. Another study out today, led by Tomoki Kimura from the Japan Aerospace Exploration Agency and co-authored by the UCL researchers, reports that the X-ray aurora responds to quieter gusts of solar wind, deepening this connection between Jupiter and the solar wind.